Thank you. Yeah, as you just heard, I am not part of the CIDER program, but some of you may have seen me kind of lurking in the shadows. That's because I'm a postdoc here, and one of the things I work on is seismology, so I'm really interested in all the things that you guys are doing, and I hope you'll be interested in what I get to tell you about today, which is seismology of Saturn. This is kind of a new stuff that I've been working on, and I only found out I was going to be giving this talk last night, at like 9 o'clock last night. And this is brand new research. I haven't given this talk before, so it's fresh off the griddle. It might be a little bit rusty, but hopefully you'll find it interesting, so bear with me. Okay, so you all know about Earth seismology, hopefully by now. Earth seismology is really great because you can put seismometers all over the planet, and you can measure all the waves. You can learn all this really cool stuff about how the Earth has all these different layers, and there's a discontinuity somewhere in the crust, and then there's another discontinuity, and then there's a mantle, and then there's a liquid outer core and a rigid inner core, and all this great stuff. We don't know all that about the outer planets. Our models for the structure of outer planets are pretty basic. We know that they have to have fluid envelopes, probably gaseous, hydrogen and helium on the surface, which kind of transitions into fluid as you go further down. And then that transitions into liquid metallic hydrogen. And then at the center, you probably have some kind of core made of rock and ice and metals. But the truth is, we don't really know. There's a big question mark in front of all these models. We just don't know. And part of the reason is we haven't been able to do seismology on on any planet other than the Earth, as far as I know. Well, it's not a planet. True. Oh, we do?
We had
Oh.
But it didn't record.
Didn't work.
Well, it worked. It didn't record. Well,
There's no earthquakes on Mars.
It recorded a lot about how the lander reacted to wind.
Okay. Okay.
You were right.
Saturn is what I'm going to talk about today. It turns out just very recently we've been able to detect oscillation modes in Saturn. So we'll see how. I should say that these oscillation modes are very difficult to detect. The ones I'll be telling you about today have periods on the order of hours, and the particles move about this far. Okay. The displacements associated with the oscillation modes are about this far. Now, that sounds easy by Earth standards. You guys are measuring, micrometers or whatever. But, from millions of miles away, that's not so easy. So, yeah.
Is the motion in the plane on the Saturn's frame or from the outside solar?
Yeah, if you're in Saturn's frame, you would see, waves about this big. Yeah. So, not very big. There actually is a lot of energy in those because these are global oscillation modes we're talking about. But it's pretty difficult to detect. Now, the reason you can do it on Saturn is because Saturn has this extraordinary system of rings surrounding it. Now, these rings are really cool. They're about 100,000 kilometers wide, and they're about as tall as I am. Maybe as tall as the room. But basically, they're a very cold, ordered system. So that means that any perturbation in the rings shows up as a disturbance in the way that the particles move. So if you look really closely at the rings, if you take a picture, they'll look something like this. You'll see all these patterns of waves propagating through the rings. And if you're really clever, it turns out these are actually spiral waves that are very, very tightly wrapped. So it's hard to tell that they're spirals. But if you're really clever, you can figure out how to measure the number of arms in that spiral pattern. And you can also figure out how to measure the frequency of the oscillatory motions of the particles in the waves. So that's something that Matt Hedman did, who's at Cornell, or was at Cornell, and also Phil Nicholson. They used a bunch of Cassini data to figure out how to do this. And so what they actually did is they wait for a star to pass behind the rings, and they measure the brightness of the star. And if the star is passing behind one of those waves in the rings, you see its brightness go up and down with time, or up and down with radius in the rings. And if you take a bunch of those measurements and you correlate them, you can measure the number of spiral arms in the wave, m, and the frequency of the wave, which I'm writing it as a pattern frequency here. It turns out the waves are only launched at Lindblad resonances. They're launched at points where the epicyclic frequency of the orbital motion of the particles in the rings matches some sort of forcing frequency, which is just m times the difference between the orbital frequency of the particle and the frequency of whatever's forcing it. Okay? So they did this, and they figured out that these waves are not associated with any known forcing. So we see a lot of waves in the rings that are generated by resonances with Saturn's moons. But they looked at some waves in the C ring, the inner part of Saturn's ring, that definitely are not excited by resonances with Saturn's moons. But it turns out that they are approximately where you'd expect them to be if they're excited by resonances with oscillation modes of the planet itself. So this is really cool. You have oscillation modes in Saturn that are ringing constantly. And at certain places in the rings, the particles are resonant with those oscillations. That launches waves in the rings, which we can then detect and measure, and thereby measure the oscillation mode frequencies of a limited set of Saturn's oscillation modes.
So you're basically talking about normal modes?
These are normal modes. Mm-hmm.
So what excites oscillation?
That's a great question. If you could tell me, I'd love to hear. But no, we don't know. It may have something to do with the fact that Saturn's outer layers, at least, are convective, just like the Earth's outer core is convective. That convection should be able to excite waves and oscillation modes. It's not clear if that's what's happening here. We know that happens in the sun, for instance. It's not clear if that's happening here, but that's a possibility. Yeah?
How are the rings coupled to?
Great question. It's gravitationally. So the only way that a mode can couple with the rings is if it has a large gravitational influence. And so that actually allows us to only see certain types of modes, which I'll get to. Okay, so we figured out how to measure a few of Saturn's oscillation modes. We can't measure very many. I was wondering, do any of the seismologists know approximately how many normal modes we can measure in the Earth? How many normal modes have we observed? 1,000? 10,000?
Yeah, let's say 10,000.
Okay. In Saturn, we have 6. Okay? So the level of sophistication here and the amount of things you can do is certainly limited. But hopefully I'll show you that even with those 6 modes that we've observed, and there might be a few more on the way, you can potentially learn some very interesting things. Okay. So here's a table of those 6 oscillation modes measured by Hedman and Nicholson. It turns out that they found 2 m equals 2 oscillation modes, 3 m equals 3 oscillation modes, and 1 m equals 4 oscillation modes. And the locations of these modes and their frequencies here, their frequencies are about a millihertz, are approximately where you'd expect for basically what we heard about earlier in the week, the football modes. These are the L equals 2, M equals 2 fundamental oscillation modes of the planet. So these are kind of the largest scale oscillation modes whose wavelength is basically the size of the planet, and so the whole planet is kind of coherently pulsating. And the L equals M modes are modes that are basically traveling around the equator of the planet. Okay, so those modes have frequencies of about a millihertz. And for a naive model, and this was actually predicted that this could happen over 20 years ago by Mark Marley and Carolyn Porco. But they only predicted that you'd see about 1 mode here, about 1 mode here, and about 1 mode here. We actually have 2 modes, very finely split in frequency for m equals 2, and 3 for m equals 3, and 1 for m equals 4. So this is very puzzling. This kind of splitting is not observed in the Earth. It was not expected for Saturn, so it might be telling us something very interesting. Now, this is not rotational splitting for all of you who immediately think that's what's going on, because that is kind of what it looks like. You know, in the Earth, you see these finely split modes due to rotational splitting. That's not what's happening here. I'm talking about modes that have the same M, whereas rotational splitting is between modes of different M. So there's something a little more interesting going on here. So what is it?
What's the
Yeah.
resonant location?
This is location in the ring. So this is measured from the center of Saturn outwards. This is important for ring people. So all these resonant locations, these are actually where the waves in the rings are observed. It's in the inner part of the rings, in the C ring. Yeah.
What depths are these normal modes most sensitive to within Saturn?
So the F modes, which is mostly what's important here, are kind of sensitive to everything. They're more weighted towards the surface, but they kind of give you a gross measurement of the density structure of the planet. Okay, so the avenue that I chose to pursue, and which I'm going to try to convince you is at least part of the solution to this problem, is that the naive models of Saturn's interior structure and giant planets in general are, well, that they're naive. That there's something more interesting going on. So the naive models are that you have some sort of core of the planet. It might be liquid, it might be solid. It's certainly enriched in rocks and ices and metals. And that's surrounded by a big convective hydrogen and helium envelope. Now, if it's convective, that means the Brunt-Bisala frequency in that region is 0. So that means you can't have a certain type of mode, which is called a gravity mode. Now, my understanding is that it's possible gravity modes exist in the liquid outer core of the Earth, but they're basically impossible to see. Is that correct? Any?
Not seismology.
Right, and I think the reason is because even if they existed, you wouldn't see them at their surface. Their eigenfunction basically goes to 0 outside of that fluid region. Is that right? Okay, so even if they're in the Earth, they'd be very hard to see. That's kind of true of Saturn, but Saturn is mostly fluid, so you might be able to have these gravity modes inside the planet, and those might be able to produce some of what we're seeing. So in particular, we know that Saturn has this kind of fluffy gaseous envelope with low density. So what I plotted here is the density structure of just a toy model of Saturn. So it's got a low density convective envelope, has a high density core, and in between, we don't really know what the density looks like. It could be a step function, as it often is in the Earth, or it might be some sort of gradual transition region. If it's gradual, then this large density gradient gives you stable stratification, which then gives you a cavity where gravity modes can propagate. Okay? Yeah.
Sorry, can I ask what makes you think the question? So what makes you think, other than the formation models, what makes you think that Saturn still has a inner core region?
Well, we know based on Saturn's gravitational field that it has to have a dense core. It has to have a big, dense core, something like 10 to 20 Earth masses. But exactly how big, exactly how its radial extent, that's not known. We know that there's definitely a region that's enriched in heavy elements.
That does depend a little bit on the equations of state.
Sure. This is a toy model. This is not sophisticated. The important thing here is that it has this stably stratified region in it. That's the most important part of this. Okay.
What's N squared?
Okay, N is the Brunt-Bisala frequency. That's what's going to be really important for the gravity modes. Okay, so that tells you the frequency that particles like to oscillate at if you poke them, the particles that are in the stably stratified region. So N is basically 0 in a convective, or close to 0 in a convective region, and it's positive in a stably stratified region. This is the sound speed squared. That has very little effect on the modes I'm going to be talking about. If you want to look at pressure modes like you see in the Earth, then the sound speed is very important, but we have not observed those types of modes in Saturn yet. Blue is just the gravity, just local gravitational acceleration. Oh, yeah, so epsilon, well, I'll get to that in a bit, but epsilon is the approximate ellipticity or oblateness of Saturn as a function of radius. Saturn rotates really rapidly. It's really centrifugally distorted. It is not a sphere, which makes all these calculations much nastier, but I'm going to ignore that for now and come back to it later.
So this stably stratified profile.
Yeah.
And where do you get that from?
I made it up.
Okay.
The goal here is to find a model that somehow is consistent with the observations. And yeah, I'm not doing the full inverse problem of taking the modes and inverting them to find a structure. There's just not enough data for that. Maybe eventually there will be. For right now, I'm just trying to find something that can qualitatively explain what we see. Yeah?
Yeah, this is a really naive question, but if Saturn is just a ball of gas, then with some stuff in the middle, how do you define like where Saturn stops and space starts?
That's a good question. They basically, I'm not exactly sure. I think they tend to just find a place in the atmosphere where the pressure is 1 bar, and they say that's the surface. And that's approximately visibly where the surface is. The scale height there is really small. It's much smaller than the radius of the planet, so it does look like a sharp transition, even though it's not perfectly sharp. I'm going to skip this slide for now. Okay, I told you what was important about the modes is if they have a gravitational influence on the rings. So what I've plotted here is several mode eigenfunctions, several normal mode eigenfunctions as a function of radius within the planet. Okay, so their angular dependence is essentially just spherical harmonics. And what I plotted here is their gravitational potential perturbations as a function of radius. So the most important mode here is this black line. This is somewhat like what an F mode in Saturn would look like. It's mostly localized in the fluid envelope of the planet. It has a very large gravitational potential perturbation at the surface. That means it's going to be able to have a strong effect on the rings. And it doesn't sample the inside of the planet very well. In contrast, these gravity modes, those G modes I was telling you about, they live in that stably stratified region, which in my model is somewhere near the core boundary, somewhere in the interior of the planet. And they have an oscillatory wave function there, but their gravitational potential perturbation near the surface is very small. So that means the G modes by themselves would be almost undetectable and would have almost no influence on the rings. But we see something there. So how can the G modes do it? Well, I'll get there in just a second. First, I want to look at kind of a frequency spectrum of the planet. So if I took away that stable stratification within Saturn, if I just looked at a naive Saturn model, this plot would be much simpler. I'd basically just have this mode and this mode. Okay, these are the F modes of the planet. This is essentially the football mode of Saturn, except the L equals 3 football mode, so the triangular football mode of Saturn. This is the L equals 5 pentagonal football mode of Saturn. All these modes are G modes. Okay, and then some weird stuff's going on down here. That's because you also get inertial modes, which are restored by the Coriolis force. I'm not going to go into those right now. They're not too important. What's important is that when you add in the stable stratification, instead of just having one mode, which is what was predicted, we now have this vast array of modes in the same frequency regime as the F modes. Now, most of these modes are G modes, and their gravitational potential perturbation is really tiny. Way too small to affect the rings. But it turns out that I've kind of swindled you here. This actually isn't this isn't a real mode spectrum for Saturn. The reason is that Saturn rotates very rapidly. And I told you I was going to leave that out at first, but it's very important when you get down to it. It rotates so rapidly that Saturn is about 10% wider than it is tall, so it's very distorted. The Coriolis force is very strong. The ratio of the mode frequency to the spin frequency of Saturn is approximately unity for these modes, so rotational effects are important. But the first thing that rotation does is it shifts the mode's frequencies. So in the Earth, you take all your different m values for the same L of an oscillation mode, and you just split them by a bit in frequency. In Saturn, that happens, but the splitting is much bigger. And the other thing that happens is if you have all these G modes, not only do the modes split, but they all start overlapping with each other. So that means the modes are no longer just an F mode or a G mode, but they start interacting with each other and mixing with each other. And if you have two modes whose frequencies want to be right on top of each other, they go through degenerate mixing, or it's also called avoided crossings. And when that happens, the two modes start to take on each other's characteristics. So if you see two modes at an avoided crossing, they will both look like some sort of hybrid mode, and their frequencies will be very finely split from one another. And so it's possible that that is what we're seeing in Saturn, that we see these waves in the rings that are generated by these hybrid modes that are a hybrid between an F mode and a G mode, whose frequencies are almost identical. So that's the picture I'm trying to put forth here. Okay, so now I have a very dense plot which embodies a lot of my results, so we're going to walk through it one step at a time. What I've plotted here is the optical depth variation produced by a mode, so basically the amplitude of a wave in the rings of Saturn launched by a mode as a function of the mode's pattern speed, or basically just its frequency. Okay, so the blue diamonds show the three observed waves in Saturn's rings for m equals 3 waves. So we have these three observed wave trains. They have almost the same frequency, and their optical depth variations are a little bit different. But these are the ones we've detected. And I should say that if your mode has a really weak influence on the rings, it's going to produce only a very small optical depth variation, and it's just not going to be observable with Cassini. So all these modes down here, they're too faint to see, probably. Also, modes at the right side of the plot have frequencies that are too high to resonate with the rings. In order to resonate with the rings, that resonance location would have to be inside of the C ring where there's no rings anymore. So we can't see the high frequency modes over here or the modes that have low gravitational potential perturbations. Okay, so now let's look at the black stars. The black stars are basically the same modes that I showed earlier. Those are pseudo modes. They weren't a self-consistently calculated mode. They were kind of a pseudo mode of the planet that helps us understand what we're seeing. So this is an L equals 3 pseudo mode, and here's all the L equals 3 G modes. Here's the L equals 5, L equals 7, etc. Okay. Now what happens when you add in the rotation self-consistently is a couple things. The first thing is you'll see this F mode frequency slide over right next to the observed frequencies. So this is mostly because I've now added in the centrifugal force. That tends to lower the frequencies of these modes. So that brings our F mode frequency to within less than 1% of the observed frequencies. So that's really nice. I think that's really nice reinforcement that tells us that the waves we see in the rings are definitely generated essentially by Saturn's F modes. Okay, but what you'll also see is that several of these other modes slide upwards. So this mode slides all the way up here, this mode slides here, and some mode from down here in this forest of G modes slides all the way up here. And the reason for that is that these modes are undergoing those avoided crossings that allow them to take on F mode characteristics and give you these hybrid F mode G modes, which are finely split in frequency and which should both be observable in the rings. So we have 3 observed waves, and 3 observed modes, these 3 red crosses here. So that's potentially an explanation for what we're seeing.
So,
Yeah.
Sorry, so the y-axis is like amplitude or sensitivity?
Yeah, it's amplitude of the wave that a mode would launch in the rings. Yeah. Tau is optical depth. So the optical depth variation that you'd see. I don't have to phrase it. I just phrase it that way because that's what we really observe. Okay, so those are L equals 3 waves. We can do the same thing with the M equals 2 waves. So in this case, there's 2 observed modes. And this model gives you basically 2 modes with frequencies that are pretty similar to the observed modes, and with amplitude variations that are also pretty similar. So that's nice. And then you can do the same thing with the 1M equals 4 wave. And so there's 1 wave that's observed. This calculation predicts that there might actually be 2 observed that could be observable. You notice I'm getting the amplitude wrong here. That's actually probably also interesting. It's probably telling. So the way I calculated these mode amplitudes is I just matched one of the M equals 3 modes, the observed amplitude, to, I just made up a mode energy so that it would give me the right optical depth variation, and then said all the other modes have the same energy. And so that assumption is certainly breaking down here. So that means that these higher frequency M equals 4 waves probably are actually, those modes are excited to lower amplitude. So that might be telling us something very interesting about what's actually exciting the modes in Saturn, which we don't know. But the point is that these models more or less qualitatively reproduce the observations. Yeah.
So, as far as I can tell, the models are based on, say, an assumed density structure.
Mm-hmm.
How unique or non-unique is that density structure? How much did you have
It's
to do?
it's certainly non-unique. You could definitely make up other structures that give you similar results. So this problem is poorly constrained. You can make up all the parameters you want. You could, yeah. The point is to qualitatively, hopefully, give something that can reproduce observations. So it's definitely not the final story. The model I showed is not the definite structure of Saturn. Okay, it's just something that hopefully qualitatively matches what's going on inside of Saturn. I should also say that to get all these things to line up, I had to fine-tune this model. Okay, so this is not a rigorous process. And in particular, I really had to do some work in fine-tuning it. Getting 3 modes up here that are all strongly mixed with each other doesn't happen. It's not very likely for that to happen in the kinds of models that I was considering, which were pretty simple. They only had about 2 parameters. So there's probably something else going on inside of here. There's a fine-tuning problem. I can't reliably get the kind of mode, the frequency splitting that's observed. So it probably means that either what I'm saying is just wrong, or that there's a piece of physics that I've left out. And in particular, one of the things that I did with all these calculations is I just assumed that Saturn was rigidly rotating. It turns out we don't even know the exact frequency at which Saturn rotates. It actually turns out to be pretty hard to measure. And in particular, it's probably at least somewhat differentially rotating, but how much differential rotation is somewhat unconstrained. But if you add in differential rotation, it's going to make all that mode mixing that I talked about much easier for that to proceed. So that's something I'd like to investigate in the future, to see if adding in differential rotation really helps us match the observations. So that's something I'm hoping to do in the future. Another interesting thing is what excites these modes. We don't see oscillation modes with amplitudes of order of a meter in the Earth. Okay, modes get damped down very, very quickly in the Earth. In Saturn, the modes live certainly for years. Saturn just rings at least coherently for time scales of at least years. And the modes are pretty large, so there's definitely a big energy source there. What it is, we don't know. And another great thing would be to observe P modes in Saturn, and hopefully other gaseous planets. that's how we do helioseismology. We look at the sun. We basically measure the shifting locations of absorption lines in the sun spectrum. We take a Fourier transform of that, and that allows us to measure P modes in the sun. People have tried doing that with outer planets, but it's much more difficult there. But if we could do it, it would really open up a whole new door into the structures of these planets. So that's something that people are working on. Hopefully it will come about in the future. And then there's all sorts of different avenues we could explore. This is just the beginning of this process. I'm hoping that it'll evolve into something much more complex and something that we can really learn about the interior structures of these giant planets. Thank you. Okay, a lot of questions. I'll start here.
So the P modes.
Yeah.
What's the limit and why we're not seeing them in the gas planets? Is it spectral resolution that's the issue, or what's the avenue for improving our ability to see something like that?
So people are working on it, and there are tentative detections of P modes in Jupiter. The problem is that to observe these things, you have to get a big telescope, look at the planet, you have to look at the sun's reflected light off of that planet, and then you have to try to filter out all the things like cloud motions. It turns out that the oscillation modes of the sun have about the same frequency as the oscillation modes of the planets, so you have to make sure you're not just getting the solar signal. Yeah, because the sun and the planets have about the same density, so the modes are at about the same frequencies. So people have tried. It's also difficult. I mean, the radial velocities associated with these modes, for the modes I talked about, they're less than a centimeter per second. You just can't really do that. The P modes might have larger radial velocity variations, but even if it's like a meter per second, that's state of the art. That's about as good as we can possibly do, and you still have to filter out all that noise. So it's tough, but people are working on it. Yeah. Yeah.
Are the rings themselves entirely passive recorders of these normal modes? Or if you integrate over millions of years, is there a net material dispersion effect, or you're depositing some energy within the ring? Is there an implication for ring dynamics embedded in this?
I think there could be implications for ring dynamics. Actually, one of the things I should mention, you'll notice I have a blue dashed line here. That's the location of the Maxwell gap in the rings. Why that gap is there is unknown. Well, one of the things I speculate about is that it's right next to one of our oscillation modes. There's a very good chance that this gap is actually opened due to a resonance with Saturn's F mode, and that these are actually just finely split submodes. Okay, so that's what I think is what's going on here. Also, over long term, yeah, you're depositing energy and angular momentum into the rings. It's going to affect where the particles go over long time scales. So there's a lot of interesting dynamics. Yeah.
So about 20 years ago, comet Schumer hit into Jupiter, and we watched that whole thing, right? So, and Jupiter has rings, as does Saturn, or Uranus and Neptune. So, like, if we could, and that seemed like that could be a nice ringing mechanism.
Mm-hmm.
So, do we have? I mean, could we look in the data that all the images that were taken 20 years ago? Would we be able to see anything? I don't know.
That's a great question.
In the rings of Jupiter.
Yeah,
Can we look? We have 30 years, 40 years of Voyagers. Maybe there's something in the data that could be pulled out.
So, well, I'll start with the rings. Jupiter's rings are pretty sparse. I don't know if you could see anything there. I'm not sure. People have looked at Uranus. There might be something interesting coming out there. I'm not sure. As for the cometary impact, yes, there's actually, after that happened, there's a flurry of papers investigating whether or not comet impacts could excite oscillation modes of the planet and allow you to do seismology. It turns out that they just aren't big enough. Yes, you put some power into the modes, but it's really not big enough to detect. So it's possible the modes could be excited that way. It just seems unlikely. I've done kind of an order of magnitude calculation, and it's
So Jim,
unlikely but possible.
Are you
Yeah.
going to be around for the rest of our
I'm around I'm a postdoc here, so I'll be here.
If I make the following suggestions, we unfortunately need to bring an AGU mentality to this. Press on your research project, your future that directly depends on our discussion. So what I would suggest is that we give Jim a great round of applause. Thank you. Be sure to catch him while he's around. What's your office number again?
I forget, but it's down the hall on the right.
So we know where you live. And again, thanks very much. Appreciate that.
Thank you.